What is TARC?
Thank you. TARC, TARC, is the American Rocketry Challenge. It is a rocketry competition that encourages students from grades 6 to 12 to participate in a nationwide competition. Students learn how to build, design, and ultimately launch a model rocket in just a few months. As a team of no more than 10 members, you are required to construct a model rocket of your own design capable of reaching a considerable altitude. An egg is placed in a chamber near the nose cone and is expected to be intact when the rocket lands. Parachute deployment timing needs to be perfect in order to meet the timing requirements, and a failed parachute can crack the egg. There are specific measurements for the rocket's desired altitude and flight time, but we'll go into that in a moment. The grand prize for winning TARC is a cash sum of $20,000 for the team and $1,000 for the school. That's for the first place, national finalists. The cash prize gets lower the further you are from first place. There are also different categories within the competition. These categories also have their own cash prizes. These categories are rocketry, marketing, and presentation. The rocketry category means exactly what you think it does. Points for how well your rocket can achieve the envisioned objectives. Marketing points account for how well you're able to present your rocketry journey by video and throughout the media. Talking about media, go follow us on Instagram and YouTube at Ashnova Tark Team. We also have to make a 2-minute video projecting our team's progress and what we have learned. Lastly, presentation points, for much like marketing points, are lofted based on your team's ability to share the knowledge of rocketry and your rocket via the medium of presentation.
As Tor mentioned, there are certain objectives our rockets must achieve. The foremost objective is to ensure that your egg does not crack upon impact with the ground. Secondly, the quality of your flight is measured by its adherence to the following qualities: an altitude of 820 feet and a flight time of 42 to 46 seconds. Lastly, the rocket's motor and dimensions must be approved and specified.
Now that we've got all of that preamble out of the way, let's talk about some rocketry and its underlying principles. That way, if we reference a specific part of rocketry or our rocket in particular, everyone will know exactly what we're talking about. Rocketry is deeply rooted in physics. So, to give a basic understanding, we'll only talk about the leading principles. First, we'll discuss Newton's first law of motion, after which we'll talk about combustion and thrust, and finally about ISP, or specific impulse, and stability.
Newton's second law. Probably the most important principle between any type of rocketry, from tiny little model rockets to giant rockets that launch people and satellites into orbit. The basic point of Newton's second law is every action has an equal and opposite reaction. A good example to this is a rocket, as you can see right there. Thrust goes downward, the rocket goes up. Another good example is a cannon, which, when the cannonball is fired forward, the cannon recoils back. This is the most basic principle between any rocketry, and it is probably the most important one to understand deeply. Because without this, thrust and combustion would literally do nothing.
Thanks, Clayton. So let's talk about what's generating this force: combustion and thrust, or to be more specific, combustion generating thrust. Scientifically, combustion is a high temperature exothermic reaction. These exothermic reactions, or explosions, expel hot gases, generating thrust, thanks to that Newton's second law we were talking about earlier. In a rocket, or in the case of a model rocket, a motor, the propellant is stored as reaction mass for forming high-speed jet fluid, usually high-temperature gas. So when you look at the diagram here, there are a few factors that go into calculating and stuff like that. First, we've got velocity, which is just essentially speed in a certain direction, so it's defined as a vector. Then we have mass flow rate. So to explain mass flow rate, I'm going to talk about so a rocket, right? You have the fuel in a rocket, whether it's solid or liquid. This rocket is losing mass the more time that goes by. So it becomes easier for it to fly the more time that passes, essentially. So essentially, mass flow rate is just the amount of mass or gas or liquid that flows in a certain amount of time. Finally, uh, there's also pressure, which is just pressure. So all of these factors go into, uh, working out the altitude and stuff like that, and what's going to happen to your rocket, essentially. So there are solid fuel rockets, which use solid fuel. Usually a spark ignites the core, which burns inside outward. And then, of course, the combustion chamber is always. Liquid fuel rocket, with a liquid fuel rocket, you've got liquid fuel and an oxidizer that mixes with that liquid fuel to create that exothermic reaction we were talking about. Of course, combustion chamber and hot gases you've got expelling out, pushing that rocket out.
Oh, sorry, I was muted. So, the ISP, or specific impulse, is the measure of the efficiency of the reaction mass used to generate thrust in a rocket engine. A very general formula for ISP in seconds is thrust divided by gravity, or the Earth's gravity, so 9.8 meters a second squared, times mass flow rate. Mass flow rate is how much propellant mass flows through the engine at any time. Looking at our example of the cold gas thruster, we can see the stored propellants expelled through the nozzle. The nozzle has area where it goes from a small opening through a large opening. The ratio between these is called the nozzle ratio. Generally, engines with a higher nozzle ratio are more efficient in a vacuum, as the propellant has more expansion and therefore more thrust. And however, a lower nozzle ratio is generally more efficient in atmosphere because air pressure pushes in on the propellant and forces it into shock cones. So if the nozzle ratio is too high, it can damage the engine.
Stability is imperative to ensure a nominal flight. Stability is also what facilitates a rocket to fly on a clean and predictable trajectory. An unstable rocket has the potential to whirl in the air uncontrollably. Stability is often measured in calibers. 1 caliber is equivalent to the rocket's maximum tube diameter. Ideally, the distance between the center of gravity and the center of pressure is 1 caliber. More generally, the center of gravity must be above or in front of the center of pressure to ensure a stable flight. As you can see in this diagram, the rocket will fly straight and stable when the center of gravity is in front of the center of pressure.
And make sure you put all of your questions in the Q&A, or you can raise your hand and we'll call on you.
Any questions? Okay, moving on.
Either? Yeah. Let's keep going then.
Now we have parts of a rocket. Model rockets usually have at least 3 common parts: the engine, which actually expels the thrust; the nose cone, which goes on the top, it aerodynamically redirects the forces; the parachute for safe recovery; and a body to use to house it all. Our rocket has much more than that. To start off, we have that nose cone up here. That is where our altimeter is housed, which mentioned earlier is how we get our altitude. It also redirects aerodynamic forces around the rocket. After that, we have our payload bay. It's this tube right here. That tube houses the egg and the egg protector, which is made out of foam. After that, we have the transition piece. Due to the rules in the competition, we have to have 2 separate tubes at different lengths. So this is how we connect the 2. Inside of the transition piece, we have our nice little parachute. That protects That doesn't really protect, but it has a soft landing. It slows it down on the way back down. Behind the parachute, there is dog bark or webbing, which protects the parachute from the heat when the engine back ignites. So after the motor is done firing, it back ignites to separate the rocket. So that protects the parachute from burning up. Next, we have our lower body tube down here. That lower body tube has the motor casing, which retains the motor in, then the fins for aerodynamic stability. We use an E35W. Is that right? Correct? You'll
I believe
learn
it's
more about that.
E35.5.
Yes,
or-
E35-5W. You'll learn more about that later. Next, we'll move on to factors we used in designing a model rocket. We had to take several factors into account when designing a rocket. First, we need to make sure that it was all compatible with the very complicated rules. I'm talking paragraphs worth of rules. Once we verified the dimensions of the rocket were appropriate, we moved on to checking other factors that were not mentioned in the requirements, but turned out to be very important. Paint, and as mentioned before, stability. Painting a rocket makes it heavier, yet it makes it smoother, so makes it more aerodynamic. Because think about this, if you have a rough surface like this, the air is going to get caught in all of this. But if you have a nice flat one that's painted like this, there's less for the air to catch onto. Stability is measured in calipers. The calibers is 1 to 5. A recommended stability is around 2. Ours is a teeny bit less than 1.57. Next, Connor will now go on about the motors.
So for motors, we are going to use an E35-5W motor, which has an impulse of 39.4 Newton seconds for qualification flights tomorrow. We went through several motors, including the F44-4, but the E35-5W got us closest to our goal of 820 feet. Next, when designing our rocket, we focused on the goals of the competition, namely launch a rocket to an apogee of 820 feet and bring the egg it is carrying down safely within 43 to 46 seconds. This has been the hardest part of the competition for us, and there were many unsuccessful attempts. However, we managed to get the egg down safely almost every time. So what do you think was harder for us, to achieve the correct altitude or achieve the correct flight time? You can just shout it out, and you don't need to raise your hands, by the way.
Actually, I have a poll for that if you want to let me.
Oh, yeah. Let's do
Okay.
that.
Should launch now. And then just put your reasoning in there, or you can raise your hand and explain your reasoning.
Exciting result.
Sorry, 1 second. Yeah. No one's answered yet.
All right, we'll give you until 1 minute and 15 seconds. If you don't answer it by then, or if you want more time, just raise your hand, but we're going to end it after then.
How about we just keep going and just leave the poll up?
Okay, that's good. A
So do you want me to
slight,
just say the answer?
yes.
Alright, so the answer is obviously altitude, because with the altitude, getting the altitude has been the hardest part for us. The rocket went ever from 730 to 960 feet, depending on what engine we were using. And this is because the altitude is dependent on what angle the rocket takes when it lifts off. If it goes straight up or to the side, that affects the altitude. Wind conditions can also affect the altitude, and as well as that, the barometric pressure can even affect the altitude. There are many, many factors that can affect the altitude of the rocket.
One slight correction, our qualification flights are happening today. All right, moving on. Design process. Our usual design process looks like this. We would make a design in OpenRocket, run a simulation, make iterations, then we would usually run another simulation. So there's almost a tiny loop inside the loop in here. But once we deemed our design good enough, we would do a test launch. Then we would go back into making a new design. We did that around once or twice. We would keep a little bit, but we'd make a pretty big design. Or if that design was ish good enough, we'll make an iteration, run simulations, and we just kept doing that over and over and over and over again until we got a rocket that we deemed good.
As you can see, here are several of the prototypes that we designed in OpenRocket. The image at the bottom is our final design, which we built. On its first launch, it flew successfully, and however, on the second launch, it exploded on the pad. The engine was broken, and we managed to repair it. However, we did not repair it well enough, and on the very next launch attempt, it burnt to the ground on the pad. This is why we decided to name our first rocket Burning Bill.
All right, next slide.
So several of our launches were not successful, but that gave us stuff to learn from. We used a bunch of data like altitude, flight time, and the weight of our rocket, and we took that all into account and learned from launches and made changes to our design. We changed things like motors and adding mass to the rocket and OpenRocket, and we also tested different fin sizes and configurations. We ran simulations of the new designs in OpenRocket and then chose the best designs. We built those and tested them in the real world. Here you see a screenshot from our data collection spreadsheet, which we'll discuss more later, showing some of the data collected from the launches, and then we use that and refine it into our new designs.
Liam?
Oh, yes. So, our current design. Using OpenRocket, we've run countless simulations and created several different designs. Every rocket is built differently, and every launch allows us to correct our design and to get us closer to our altitude and flight time goals. We adjusted the simulations for the wind speed, altitude above sea level, atmospheric pressure, and temperature, among other things, all according to the conditions just before launch. That's so we could get the most accurate results possible. However, OpenRocket is not perfect, so we carefully analyzed each launch's results and estimated the margins of error. Then we could adjust our design accordingly. We triple-checked our current design, including the motor used, to make sure it satisfies all the requirements of the competition. The last thing anyone wants in TARC is to get disqualified because their rocket is half an inch too short.
We learn something new from every launch, which is why 15 plus launches are usually done before qualification flights. That's imperative to this process. We've done just over 10, which is cutting it a bit short, and our most recent launch happened just last week. This was our last attempt before qualification. It's happening today, our last attempt before qualification flights. So a lot is riding on. Fortunately, we saw an outstanding performance from our rocket using the E35.5 motor. That's the motor we're going to use again in qualification flights, which are today, with just luck. A score under 30 is usually needed to be one of the 100 teams to get into the finals, and we achieved that last launch. We have a good chance. Besides, even if we don't win the finals this year, we can always try again next year. Silas, take it away.
Thanks, Kalel. One of the largest contributors to our success is our extensive data. As you know, our team is spread across the US, which means we're unique in the fact that we're a solely virtual team. This means that only a few of us were able to see the launch live, and even less were able to build the rocket. Of course, we recorded the main factors, such as egg weight, rocket version, the time, and altitude. But early on, our team decided that it was paramount to record additional data. This traditionally non-important data helped us find why our rocket was going higher or lower than expected, why the flight time was completely different from the simulation, or why the egg cracked. We also specified what the optimal launch would be. This allowed us to change our rocket based on the best possible case scenario. and soon we have 10 launches worth of data. This data helped us design, redesign, and redesign our rocket again, all with higher efficiency. And then for the marketing component of the competition, we mainly use DaVinci to edit and produce our videos, as well as Blender to make animations for said videos. And we use DaVinci videos for our Instagram, YouTube, and some short form vertical videos.